All right, so now that our definition of a logarithmic function has now been extended to include these functions to be also regarded as a logarithmic function here. Any function in the form of a constant coefficient multiplied with a log base a of some linear expression mx plus b. Okay, and plus with a constant term k here. So now in our extended definition, we include any of these functions here as a logarithmic expression. And so as a matter of fact, this is now a more like a general form of a logarithmic function in our understanding up to this point. So in that way right here, in this way that we extend our definition, then let's see how a logarithm function in this complicated looking can change the graph right here. Because now ultimately we have already learned that log base a, the simple log base a of x right here, for whatever base that is, as long as the base is a positive value and other than 1. So for any function being just this simple logarithm, then the graph is a rising one-way curve, asymptotic at the y-axis and intercepting with the x-axis right at 1, 0. Okay, and it's a rising one-way graph from the left to the right with this shape right here when a is a value greater than 1. And then on the other hand, this same form of the function of a log function, if we're looking at a base where it's less than 1 right here but still positive, then our graph is a falling graph from the left to the right but still asymptotic to the vertical y-axis here and having and intercepting with the x-axis right at 1, 0 again. Okay, and then the domain and range stays. This is domain here is any one of these two cases is having domain anywhere between 0 and positive, as we have learned up to this point. So now what we want to know is that how will something like this be changed, be transformed from the graph of ultimately a simple function log base a of x right here. Now I start using that term be transformed because simply what we recognize here is that any function in this form right here is simply just a matter of see, we have a linear expression inside of the log, so this coefficient here is in some way responsible for a horizontal scaling, as combining with what we have learned in the past, specifically on the transformations technique from a function. And so this is some coefficient inside our log function that explains for some horizontal scaling, and then this is responsible for some horizontal shifting. Okay, and then this is going to be responsible for the vertical scaling, and this is going to be this constant term at the end right here is responsible for some vertical shifting right here. So there are always 4 transformation steps that can be applied to any function. And so now we want to investigate a little further to see how a function that is in a more involved way, okay, a log function with having more things involved compared to the original, for the simple version of a logarithm function like this. How we want to know how a function like this can be changed as far as the graph compared to its original parent function. Okay, because so specifically we want to think about what is a function as a quick little example right here. What is the graph of something like this? We want to find out. So how about the -2 times log base 5, okay, of a 1/2 x minus 1 and then minus 3, for example. See, something like this has a lot more than just the simple. So if something like this, we want to compare that with the original function where it came out from a log base 5 of x right here. So we want to see how the graph of something like this, okay, can be done as a transformation out of a simple function like that. Or we want to see how this general form of a logarithm will change the graph from its parent function as a transformation. All right, because so we've learned all of that transformation techniques right there. So now we can bring our understanding into and apply that right in here. All right, so that's the idea. All right, so in what we wanted to know there, in what we wanted to learn about that, how, you know, the graph, I mean, how the function of a more general form of how a general logarithmic function can come to a graph here, and how the graph of the form logarithmic function relates to the graph of a beginning simple logarithmic function. Then now let's bring that into a further example. Here I call it example 5 here, where we want to apply our understanding of the transformations into a logarithm function. Okay, so now in this example, let's call that example 5. All right, so we want to graph. Okay, we want to graph the following function. Okay, by recognizing it, okay, as a transformation. Okay, as a transformation from a known function. All right, as a transformation from a known function. All right, so those are a couple of terminologies that a couple of terms that I want to underline like that. So we want to see the graph, we want to see the graph of whatever function about to be given here as a transformation from some known function. Okay, and so now let's bring it in for our first problem in this example 5 right here. How about f of x equals, how about I have a 3 times log base 2, okay, 3 times log base 2 of a minus 2x plus 6, and then minus 1. All right, so here we go. Welcome to aboard. Welcome to our first graph of a general form logarithmic function. It has a lot involved, but in the end, it's still within that form where I stated earlier. The function we are about to graph is still in the form of where we have a logarithm that applies on a linear expression. So what is the linear expression being recognized here in our function? The linear expression we see here is a log base 2 apply on that linear expression minus 2x plus 6. Okay, and then outside, once we're done with that logarithm, taking log base 2 operation on the minus 2x plus 6, we are going to multiply that outcome with 3. So this 3 now is acting in place of the constant coefficient c in our general form of a logarithmic function. And then we subtract 1 as a constant term. All right, so there are a lot going on in this function, admittedly. But once again, I just made it clear that this entire function is just simply one among those we call the general logarithmic function. Okay, and so now let's look back a little further into the wording of the problem. The wording is asking we want a graph. So this is, at this point, anyone is already fluent with the idea of transformation and bringing transformation into a graph. So I'm not going to really make you sketch this by hand, but ideally this is how we're doing it if we were doing it by hand. So I'm going to speed up the process a little bit, but I'm still going to show all the guiding points once we have recognized a parent function, a known function. The idea now is that we want to see this function as a transformation. Now, up to this point in our learning, as far as transformation, there are always 4 elementary transformation steps like that. Okay? On the horizontal axis, there's a horizontal scaling, either compressed or stretched. Only one of the two. Okay? That's why I call horizontal scaling. And then there's, once we scale, there's a horizontal shift, left or right. Okay, and horizontal scaling, there's also a horizontal flip. We flipped around the vertical axis like that. Okay, so that's all included under the horizontal transformation. So horizontal transformations, there are 2 elementary the horizontal transformations. And then after getting all of the horizontal transformations done, we're going to have the vertical transformations. We can scale, we can vertically compress, vertically stretch. That's all referred as vertically scaled, including vertically flipped through the x-axis. Okay, and then after we've done all the vertical scaling, then we're gonna have a vertical shift. Either are we taking the graph, shifting it up or shifting it down. So 4 major or 4 elementary transformation steps are always being involved, can always be recognized in any of these functions. All right, and so that's why now at this point, back at this problem, when I'm saying recognizing the graph as a function, as a transformation from a known function, this word transformation, even though in singular form here, it really means it's a sequence. It's a sequence of all of those 4 elementary transformation steps. Okay, and so now in that way, I already kind of broke it down earlier. When we're looking at a logarithm function like this, or specifically, let me get back to the other board right there. Now, admittedly, that the function we're about to graph is in this form. Then anytime we're about to graph a function in this general form for a logarithmic function, then we want to, this is a good hard rule for anyone learning about this. You see, I will definitely tackle right down to, as far as breaking it down as recognizing how this function is related to a known function. So that known function here, I would definitely regard to that as focus right here on that base a of the logarithm base a. So I'll just simply take that log base a of x. I would call that as a known function, because with something like this, we don't need, at this point of our learning, we don't even need a graphing device. We don't need a graphing utility to get us here. As if a is a value greater than 1, we know the graph is going to go through the x-axis like that as a rising graph. And having, at least without the need for precise scaling right here, then I just already know that the graph here must go through the x-axis at 1, 0. Okay, and it has this shape right here. How bent down, how bent up, that's just pretty much the precision of the scaling. Not too important anymore, but it's having a vertical asymptote. It's asymptotic to that vertical axis there. So that's what I meant by this. A function like this now is generally known because we already learned so much of the major characteristics or something like that. And this is specifically when a is greater than 1. Okay, and then on the other case right here, again, the reason that I say a function like this, just generally any log base a of x is considered as a known function compared to any one general like this. Simply we know this function because if now a is less than 1, the graph will definitely have to be a pointing down graph, falling from the left to the right, intercepting the x-axis at 1, 0. Again, okay, and has that asymptote, vertical asymptote, right at the y-axis. So we already knew so much about any of these simple logarithmic functions. And that's why now I see, even before I get into specifically one problem, I just want to really just tackle down, there's one good rule of thumb. That anytime we're about to graph a general logarithmic function, that known, and graphing it by recognizing it as a transformation of a known function, that known function, okay, very high chances, this function right here, log base a, or I say very high chance because I want to leave some room for maybe someone else is gonna to have some other way of thinking, but quite definitely that it has to be the simple log base a of x coming out as a known function, where in our language we usually call that the parent function. The parent function is here, and then this is just basically a descendant function. All right. And so now, once we nail this down, once we nail down this generality right here, this is a good rule of thumb right here. I'm going to get back to the other board. So now, in that way, how I explain it, let's observe it right here. So the linear expression inside of our function here is mx plus b right here. So m is minus 2, x is that's just that variable input right there, plus, mx plus b, so minus 2 for m, plus 6 for b right here. But our log here, most importantly, our log here is a log base 2. We take log base 2 operation on this linear expression. And then once we're done with that logarithm, we're going to multiply with a constant coefficient 3. And so this 3 right here is playing in place of that, is being in place of that c constant coefficient. Okay? And then this minus 1 here is a plus k, so k equals -1. So now here's how I see it. Just along with what I explained earlier when I was on the other board. Now I'm going to say, I will say that my known function, see, recognizing the function here as a transformation from a known function, So we have to first know what known function that is first. And so that known function is indeed. Now, allow me to correct some of my, I would like to correct the following. How about right from start, allow me to call this the g of x function. How's that? Okay, because it's just me, it's just my style. I always want to use the parent function with the symbol f of x. And then any of the descendants one will come out as some other name. All right, and so how about for the known function? F of x, let's call that log base. Now it's very reasonable to take log base 2 right here. So now log base 2 of x, this is a known function, and we can regard to that as a parent function. All right, so once we have identified the known function, so now once we have identified that known function, then here's what I see about it. So let's tackle right in this portion right here. G of x, in the way how I see it, this g of x, yes, it's a function in the end, a function in terms of x input. But how is this g of x related to the parent function here? This g of x is the function f, but instead of, see, and we've had that example right before this, and I purposely brought that example in before this example as well to get you comfortable with the idea that with a function known as a logarithmic function, now we can, if we simply change the usual input from an ordinary x to some expression of x, then that's going to produce something like this. All right, so that means now on the opposite way, I recognize log base 2 of this linear expression as the function f, taking input as minus 2x plus 6. All right, and this is why, I brought in that example 4 earlier to, once again, to have my student at least to also realize that, if once we have had a function, the f defined as a simple logarithmic function right here, taking an input being, an expression instead of an ordinary number can lead to something like this, another larger expression with log involved right here. Okay, and so now, but now thinking in terms of a transformation, then g of x here is the function f that takes the inputs as minus 2x plus 6. So f of minus 2x plus 6 is the same as log base 2 of minus 2x plus 6 right there. All right, and so, but then this is not all for the function right here. So what about that 3 in front? So that means now whatever the outcome of this f of 2x plus minus 2x plus 6, I am going to multiply that output there by 3. And then now I'm going to multiply, I'm going to subtract all that here by 1 right here. All right, and so now that here, this line right here completes our relationship between, this is what I call the descendant function. Now back in my the lecture where I was teaching specifically about how we operate with transformations, and I usually do this with blue ink right here. Okay, this is blue ink right here, and then this original parent function is indicated in red ink. All right, but now sadly I don't have the blue ink available immediately right now, right here with me at this moment. So I'm moving everything in. I'm rolling with everything in just black ink right here. But now, for this entire expression right here, now I see this is dm, and this now responsible for horizontal scaling. All right, that is responsible for horizontal scaling. This is responsible for horizontal shifts. All right. This value 3 right here is responsible for vertical scale or vertical scaling. Right? And the last one here is responsible for vertical shifts. All right, and I apologize if my writing happens to look a little too squeezed out right here. All right, because I have a very limited board space. All right, but then once we understand that there are going to be 4 elementary transformations involved in this problem right here, because our function g is related to the parent function f of x by applying the 4 elementary transformations here. Then now let's get started. All right, so now once we get down to the actual, applying the transformations right here, then we get back to using the common the guiding points from the parent function. And also, before we even get to that, allow me to remind anyone who's about to do a transformation. It's always better to rewrite the following. So we have g of x here currently recognized as 3 times f of the minus 2x plus 6 minus 1. But now right here, that inputs where we put inside of our function f. Okay, this linear input right here, this linear expression as the input. It will be extremely beneficial if we're rewriting this in factor form, where we factor out that coefficient with the x right here. In other words, minus 2x plus 6 is factored as minus 2 in parentheses 6 minus 3 right there. All right. And so now I'm going to change this to brackets. So that now is making it so clear that this value here is, yes, it's responsible for the horizontal scaling, but this value here truly is how far we're shifting. And then, well, that sign there has some explanations as well. Okay, and then once we're done with that, then it comes to the vertical scaling and the horizontal and the vertical shifting right there. So again, this is horizontal scaling, this is horizontal shifts in precise value right here. Okay, and then this is vertical scaling and then vertical shifting. All right, and so now, before we really get into doing that, let's now show the guiding points on our original parent function. Again, remind yourself that our parent function is log base 2 of x. F of x equals log base 2 of x right here. Okay, so now with my decimals right here, on my graphing utility with decimals, this is the graph for log base 2 of x. Okay, and it's just exactly as we expected. It's in the shape of a curve that's bent and rising from the left to the right. It has a vertical asymptote right at x equals 0, which is the vertical axis right here, the y-axis. The graph itself is intercepting with the x-axis right at that point 1, 0. Okay, and so now with this graph right here, then we can see right through our eyes that there are a few points under this graph here that falls right on the grid. Okay, making it easy for us to do the transformations. And so right there, I call those the guiding points right there. Okay, so now allow me to use the following guiding points. So again, just like how I explained before when I was still teaching about how to apply transformation, just like how I explained in my transformation lecture like that, then the idea of the guiding points really is not anything as a rule. It's just simply we picked out a few points right from our graph. Those points right from our parent function's graph. Those points are the easy points. They fall on the grids. They are easy to calculate. And then they define those points together, define the shape of your graph, the unique shape of your graph. That's what I call the guiding points, so that we can apply our transformations on those guiding points without doing that for all points on the graph. That's the idea. Okay, but other than that, really nothing fancy about the idea of guiding points. Whatever I choose as my guiding points, you can also pick your own guiding points, even though we are talking about the same graph, the same function. All right, and so now again, let's get back to the the graph right here. So now allow me to choose my guiding points as following. All right, and now let me show the label. So for my guiding points here, how I see that here, this is 1/8, comma, -3. Decimals, my graphing utility only show that in decimals right here. So 0.125, but this is really 1/8, -3. This is 0.25, which or the same as a 1/4. So 1/4, comma, -2. The next one here is a 1/2, comma, -1. So these points are not really, well, they're still on the grid, not on the complete grids, but they're still on the grid somehow, and they're still easy enough to place them in the right position. Okay, and now this one here is that famous x-intercept, 1, 0. This point is right on the grid right here, 2, 1. There's another point right here right on the grid, 4, 2, and there's another one right on the grid right here, 8, 3. So we have, I use these 8 guiding points right here. All right, and so now I am going to show just exactly like how we were doing that with in our lecture about the transformation. I am now going to construct a table of values, but not the table of values for sketching the function. It's the table of values that list the pairs of values for these guiding points. So how about let me keep the graph here on the corner of our board right here. Okay, so we want to put those guiding points as pairs of values on our tables here. And then we're going to use a table to follow the steps in the transformations. Okay, so now as far as the table over here. The first column is famously for those original points on the parents function. So the original point I see right now, I see on the graph, from the left to the right, I see a 1/8, and then that comma -3. Allow me to write small so that some writing won't need to be hidden behind that graph right there. Okay, and then I'll have a 1/4. Okay, and then comma -2. All right, and I'll have a 1/2, comma -1. All right, and now, unfortunately, I really need to hide away this graphing space right here, and feel free to roll back to this particular instant right now and pause out to take notes on your guiding points, or you can even have a duplication of this particular picture right here, right on your note-taking paper right there. Okay. And so now with my next point right here, I'm looking at, so there's a 1, 0. Okay, and we don't have to do all of these points as well, but I feel like if I go through all of these points together from afar, they are good together to bring up the shape of our graph. So it's just me that I want to use all of these 4 points. I mean all of these the 6 points, 7 points like that. Okay, but for anyone who's better at drawing than me, you can only just rely on 4 points or 5 points. That's the most like that. But most definitely get that intercepts right down. This is the x-axis right there, the x-intercept right here. Okay, and then we have 2, 1, and we have a 4, 2, and I have another one here. Okay, and then 8, 3. All right, so that should be enough for our guiding points right there. These are the points that we recognize right from our parent function. All right, so the first step now is, again, the first step is to get the function where it's in the form of f of minus 2x. So this is a coefficient that multiplies with the inputs inside of our function. All right, so now recall from our learning. Anytime we multiply a coefficient to the inputs, or anytime we have the inputs being in the form of an ax, okay, then really we're gonna multiply every x value by 1/8. Well, this is, well, so far in this lecture I call it mx plus b, but as far as the transformation understanding, this is that coefficient in front of the x. So 1 over that constant right here is the value we multiply to every x. And so 1 over a is going to be, okay, 1 over minus 2. Okay, in this particular the function right here, I call that it's the m value indeed. Okay, so maybe let's call it 1 over m. This is m right here. So 1 over m. So 1 over m is the same as 1 over negative 2 or minus 1/2. So what do I do with this minus 1/2? I am going to multiply every x value with a negative 1/2, with a negative 1/2. So by doing that, it's going to change all of our x values of all these guiding points right here. So the first guiding point is going to become negative 1/16. All right, negative 1/16 comma negative 3. So nothing happened to the y values. Okay, because this information, this transformation only causes changes to the x values. So now minus 1 over 8 comma negative 2. The next point here, the x value here is multiplied by a negative 1/2. So that's once we calculated that value right here, every x value is multiplied by this negative 1/2 right there. Okay, so now we're looking at the negative 1/4 comma negative 1. The next one here we're looking at negative 1/2 comma 0. The next one here I'm going to have a negative 1 comma 1, because 2 multiplied with negative 1/2 gives me negative 1. Okay, and the next one here I'm looking at negative 2 comma 2, because 4 times negative 2 equals 2. Equals negative 2, and then the y value stays the same. Okay, and then now 8 times negative 1/2 is a negative 4, so negative 4 comma 3. So these are the this is what the guiding points previously from the parent function become. Okay, after taking minus 2x, taking the minus 2x as the input of our parent function. Okay, and so now once we're done with this horizontal scaling step right here, this is horizontal scaling. We're going to move on to the next step where we're going to produce, we're going to calculate the guiding points. We're going to produce those guiding points where it's minus 2 times x minus 3. All right. So we're going to produce a column that lists down the values of the guiding points where it's f of negative 2 times x minus 3. Okay. So I recognize this as a horizontal shifting, but easiest way of thinking, we're going to add every x value from the preceding step here by 3. So the minus sign here, again, from our understanding, the minus sign reminds us that the minus sign is an indicator that we have a shifting. Okay, and then aside from that minus sign right there, the value here is a 3, a positive 3. So being a positive 3 here, again, the minus sign is just to indicate a sign for shifting, but the 3 here is positive, minus a positive number, so we're shifting it to the right hand side. Okay, so minus is actually not because it's negative, it's minus here is indicating, or it's a sign indicating that we have a horizontal shifting, but shifting left or right depending on the sign, the actual sign of this value. So it could be minus negative 3 as well. That's together making it a plus 3. All right, so now I'm going to add 3 to every x value from the very preceding step like that. Okay, so that means for my first guiding point, minus 1 over 16 plus 3. Okay, minus 1 over 16 plus 3 is going to give me 47. Okay, over 16. All right, and then comma negative 3. So this negative 3 came from the y value, which was not changed, but 47 over 16 here came out from minus 1/16 plus 3 like that. All right, and so now in my next one right here, I'm looking at minus 1/8 plus 3. So, and minus 1/8 plus 3 right here is going to give me positive 24. Positive 23. I wrote 23 divided by 8. All right, and then comma negative 2. The next one here, okay, minus 1/4 plus 3. So that gives me 11/4, okay, comma, negative 1. The next one here, minus 1/2 plus 3, gives me positive 5/2, comma, 0. All right, the next one here, negative 1 for x, okay, plus 3, now it gives me positive 2, comma, 1. For the next one here, negative 2 plus 3, it now gives me positive 1, comma, 2. And then minus 4 plus 3 here gives me a negative 1, comma, 3. All right, so nothing changed with the y values at all. But now with the first two columns here, see, we always do the horizontal scaling first, then horizontal shifting, and then the next, now, and after being done with all the horizontal transformations, now we're gonna blend in with the vertical transformation, where vertical vertical scaling comes first, comes before vertical shifting. All right, so in my next column, I'm gonna have 3 times f of minus 2x plus 6. Okay, allow me to write in small space so that it gives me enough space to write right there. All right, and so now all the x values stay the same, just the y values are being scaled. So every y value is multiplied with that constant coefficient. So now I'm looking at 47, comma, 16. So 47 over 16, comma, negative 9. The next one here, nothing changed to the x value. Okay, no change to the x value, 23 over 8, comma, negative 6. For the next one here, 11 over 4, comma, negative 3. Okay, and then now I'm going to pick up the pace right here, 5 over 2, comma, 0, because 0 times 3 is a 0. And then now the next one here, 2, comma, 3, because 1 multiplied with 3, we got 3. And then the next one here becomes a 1, comma, 6. And the last one here, negative 1, comma, 18. And I mean 9. All right, and so now we're so close to being done, right there, very close to being done, almost done. All right, and so now I do have some, on this part of my board, I do have some the blue markers. So now allow me to write down the last step right here, where this is also our final guiding points. So this final guiding points is for, see, 3 times f of the minus 2x plus 6 minus 1. So this minus 1 here is important. This minus 1 here means we are going to, this minus 1 right here, we're going to subtract 1 from every y value of the preceding step, of the very preceding step right here. So that's why now I'm looking at 47 over 6, nothing changed, over 16 actually, nothing changed to the x values. So minus 9 minus 1 is comma, negative 10. All right, we've got our first completed, our first final transform guiding points here as a descendants one. So descendants is in blue color. All right, and so now the next one here, 23 over 8, comma, negative 7. The next one here, 11 over 4, comma, negative 4. Okay, negative 4. The next one here is a 5/2, comma, negative 1. The next one here is a 2, comma, 2, because 3 minus 1 right here ended up with 2. The next one here is a 1, comma, 5, because 6 minus 1. And then now the last one here is negative 1, comma, 8, because 9 minus 1 equals 8. So these points in blue right here are what's going to be plotted with be put on the grids with a piece of graphing paper right there. And I will use Desmos here with my graph for this original parent function log base 2 of x already present there. Okay. And so now this is our graph of the parent function log base 2 of x with the guiding points being displayed here. All right, so now let's show the guiding points of, let's show the transform guiding points right here. All right, so these are the guiding points. Now at this zoom level, I admit that it's not able to show all of the guiding points. So let me zoom it out a little further. All right, so now with a good enough zoom level over here, these are all the 7 guiding points being displayed now. Okay, from the left to the right. So the shape looks opposite with this original parent function at this moment right here. All right, and so now let's go ahead and sketch the graph. All right, so now from the left to the right, I am going to draw the shape through, okay. And now I'm going to extend that a little further. All right, and so now if we were sketching that by hand, that's how it's going to look like. All right, so that is the graph for our, all right, so that is the graph for our, this is log base, this is 3 times log base 2 of minus 2x plus 6 right here, and minus 1. This graph in blue right here. And let me also show the guiding points to make it real clear about these values. All right, so this point right here is equivalent to, this point right here is equivalent to 47 over 16 right here. This point is equivalent to 23 over 8. This point right here, I mean these are the x values, and so this x value at 2.75 right here is equivalent to 11 over 4, and this one right here is for 5 halves. 2.5 is the same as 5 halves, and then we have 2 comma 2, I have 1 comma 5, and then I have a negative 1 comma 8 right here. So these are all consistent with our calculated guiding points on the table earlier. All right, so now we are ready for another problem where we want to obtain a graph. Either we can sketch it. I really try to make it look like we were really sketching by hand right here, but in these days, more like, we make technology, we're gonna pop out with a graph using technology, and we want to be able to verify if it's consistent with our understanding. But I'm still gonna follow through that process like we were really sketching it step by step with paper and pencil. Okay. And so now part B of the example, our function is going to be the following. How about this time g of x equals minus 2 times log base 0.05, okay? Or I mean 0.5. So minus 2 times log base 0.5 of, this is 1/3 x, okay, plus 1, and then plus 1. So the 1/3 x plus 1 is inside the parentheses as one linear expression, being the arguments of our log base 0.5 function, like that. And now after that outcome here, we're going to multiply that outputs there with the minus 2 coefficient, and then with a plus 1. All right. So now from what we already learned as an experience through part A and through some explanation I've done prior to getting into this example, and now clearly the known function, that parent function, that known function can be decided as the following. The log base 0.5, right? The log base 0.5. So the parent function is log base 0.5. So log base 0.5 of x. Tackle right down on that one, log base 0.5 of x. So with log base 0.5 of x, let's have a look at that shape right here. Let's have a look at that function. Even though, see, I said I'm very sure, I'm over 90% sure that anyone viewing this lesson at this point know what the shape of that log base 0.5 is in our throughout after what we have learned. Okay, so log base 0.5 is gonna have to be a shape going down like this from the left to the right. Okay, asymptotic to the y-axis. All right, and intercepting with the x-axis right at 1, 0. All right, so now on my graphing space with decimals here, this is the graph for log base 0.5. All right, so log base 0.5. And so now I am going to pick a few from this. I am going to pick a few guiding points. So now my guiding points are chosen as following. This is point 125 equivalent with 1,8 here, 1,8 comma 3. This is 0.25 comma 2, okay, or the same as a 1/4 comma 2. And this point right here is 0.5 comma 1, or the same as 1/2 comma 1. And these are all the guiding points that stays right on the grid. Where this point right here particularly is that the x-intercepts that I spoke about a lot. All right, and so now those are the guiding points I'm going to be using to apply the transformations. But now I'm going to get back to the board here to write down the relationship, because this is the function g. But how can we express this as a transformation or a sequence of transformations from that parent function? So very similar to part A I've done right there. So now, but here I got my blue marker this time. So the parent function is the log base 0.5. So now in blue marker, g of x, in old language where we've learned that from the transformation lecture, then I call this the descendant function. That's parent, that's descendant. Okay, so the descendant function is simply the parent function f, but taking the inputs 1/3. So think about having that 1/3 x plus 1 being placed inside right here. All right, but this time drawing some better experience from part A right here. Here's what I'm doing. We want to, for the later work as well, we definitely want to factor out this 1/3, the coefficient, and so our linear expression that we place inside of the parent function here appears in the following form. Now I'm looking at a 1/3 and then multiply with, in parentheses, x plus 3. All right, so this is now clearly we have a 1/3 coefficient responsible for horizontal scaling, and then this 3 right here. Now wait a minute, it's not exactly minus 3, so plus 3 right here is the same as minus, because the minus is making it clear that there will be horizontal shift. But writing from a plus 3 to a minus 3 means it's minus -3. So this -3 here is indicating that we're going to have a horizontal shift by -3. Okay, meaning we shift to the left. That's the idea right there. So anytime that we're having horizontal transformation, make sure we think of that as a minus the amount of horizontal shifting right there. Okay, and now further, that's -2 coefficients multiplied in front of our parent function, and then we're going to add the constant k. So the constant k is k equals 1. So now I have, so clearly this, okay, so clearly this is now for horizontal scale. Okay, this is responsible for horizontal shifting. All right, this is responsible for vertical scaling. All right, and then this is responsible for vertical shifts. All right, vertical shifts. All right, so now that should be enough. Let's tackle right in. All right, so now I am going to draw, that table. I'm going to construct that table where it lists all of the guiding points from the parent function, and then we're going to start producing the sequences of transformations applied on those guiding points as pairs of values. So here's my table. All right, so very first column right here, this is for f of x. And so now after I finish reading all of these guiding points from the parent function, I'm going to quickly pop it on screen for anyone else to view those. So what I have here is from the left to the right, I have a 1/8, okay, comma 3. That's my first one. And then I had the next one here was a 1/4, all right, comma 2. And then for the next one, I have 1/2, comma 1. All right, and then it came the x-intercept 1, comma 0. And then I have the next one here being 2, comma -1. Okay. I have 4, comma -2. All right, and the last one here on my list, I have 8, comma -3. Okay, and so now after finish writing it down, these are all the guiding points on the parents function. Let me quickly pop it in right on the screen right here. Okay. All right, so once again, these are the guiding points. That first point right here is 1/8. So 1/8, comma 3. Then we have 1/4, comma 2. Then we had a 1/2, comma 1. And then 1, comma 0, 2, comma -1, 4, comma -2, and then 8, comma -3. Those are the guiding points right on the parents function. And so now, according to what I wrote earlier on the other board right there, this descendant function g is f of 1/3 times with this expression. So that means now I'm going to produce in my next column on the table over there, I am going to produce a version, a transform version where it's f of 1/3 x, f of 1/3 x, x multiplied with this coefficient m right here, this m coefficient. Okay. And so now I'm going to create a version for f of 1/3 x. So this is my m coefficient. So that means to calculate these values right here, to see how that affects our guiding points, think about every x value is multiplied by 1 over m. So m is a 1/3. So 1 over m is going to be 1 over 1/3, which produces 3. So we're going to multiply every x value by 3. Okay, so now we have a clear direction. So on that x value right here, on that first guiding point, the x value becomes 3/8, comma 3. Nothing changed the y, only the x changed from 1/8 to 3/8 like that. All right, and then we had 1/4, so 1/4, comma 2 becomes 3/4, comma 2. Okay, 1/4 multiplied with 3 right here, and that becomes 3/4, comma 2. And then the next one here, 1/2, comma 1 becomes 3/2, comma 1. And once again, nothing changes. Nothing changes for the on the y values. Only we saw the changes in the x values, because that's the way it is. Right now, everything that we're doing is changing the x values of our guiding points. The x value of our guiding points like that. Okay, so now the next one here is going to be 3, comma 0. 1, comma 0 becomes 3, comma 0. The next one, 2, comma -1 becomes 6, comma -1. So every x value is multiplied by 3. And now the next one here, 4, comma -2 becomes 12, comma -2. Nothing happened to the y values. And then now 24, comma -3. After multiplying 3 to that positive 8. All right. And now I can put this away. Let's advance to the next step where I'm going to produce the transformation where it's the parents function, but we're taking 1/3 times x minus -3. All right. F of 1/3 in parentheses x minus -3, x minus, so this is showing that we're going to have some horizontal shift left, shift right. So how do we know where to shift? It shifts to the left by 3, but to the left, that's what it is. Okay, so in the problem it was x plus 3, but plus 3 means minus a -3. That's one more time you got to recall from your learning about the transformation, the way how we want to make it appear like that. the minus here is to ring a sign, is to ring an indication that there's a horizontal shifting. Okay, and then how far shift and in which direction of the shifting, that's indicated by this number. Okay, and so now let's calculate it. And once again, everything here in this column is going to be showing some change on the x values. Every x value is added by, see, it's a little counterintuitive right here. It's a subtraction here, but we're going to add that much. So we add -3 to every x value. We add -3 to every x value. So 3/8 plus -3. Okay, 3/8 plus -3. So that gives me minus 21/8, 3. All right, so 3/8 plus -3, okay, becomes a minus 21/8. All right, and then the next one here, 3/4 plus -3. 3/4 plus -3 becomes a -9/4, 2. So nothing happened to the y value so far. Only every x value adds -3. We add -3 to every x values. Okay, and then 3/2 plus -3. 3/2 plus -3 gives me -3/2, -3/2. Okay, comma 1. All right, and now 3, 0 becomes a 0, 0. 6, -1 becomes a 3, -1. Once again, only the x values is added. Only all the x values here are added to -3, but nothing changes the y values. Okay, and then the next one here becomes a 9, -2, and the last one here is a 21, -3. All right, so we're done with one more step, and this is the horizontal shifting right here. One more step is done with all the horizontal transformations. So we now are all done with all horizontal transformations. The horizontal scaling is here, horizontal shifting is here, and always shifting happens after scaling. Okay, and then we're doing on the horizontal scale first. I mean on the horizontal axis first. We do all the transformation on the horizontal axis first, and then we do the vertical transformations. So now here it comes the next one. So allow me to write it as minus 2 times f of, now allow me to write in complete form right here. It's a 1/3 x plus 1, because see all that here really when we multiply it out, it's 1/3 x. This is and then multiply that here, it's plus 1. That's how I get it. Okay. So at this point right here, this is the factor right here. We're going to multiply every y value, okay, by -2. So now the first point becomes minus 21/8, comma, now minus 2 times 3 right here is minus 6, okay. Minus 2 times 2 right here is a -4. So the next point here is -9/4, 2 becomes a -9/4, -4. So now now the changes only happen on the y values. Nothing happens to the x values any longer. That's the idea again, okay, about all of those transformations that we have learned. So now I'm going to pick up the pace, really pick up the pace here. All right, so minus 3/2, -2, 0, 0, becomes 0, 0 still. 3, -1 becomes 3, +2. Okay. 9, -2 becomes 9, +4. Okay. And then what we have here, 21, -3 becomes 21, +6. That's how it's done right here. All right. Now one more step. Now we're ready for the last one. This is after all of the vertical scaling. Okay, we multiply every y value with -2. So the last one is waiting for us. Okay, and we're almost completely done right here. So the last one now is -2 of f of 1/3 x plus 1, and now I'm going to add 1. Okay, I'm going to add 1. So this plus 1 right here is going to add 1 to every y value from the preceding step. All right, so now, and this is our final step right here, so now it's a good time to write in all of these points right here, these transform points in blue ink, in blue color. So now I'm going to write that as the first point, -21 over 8 comma -6, now becomes -21 comma 8 over -5. -5, okay? The next one here, -9 over 4 comma -4, now becomes -9 over 4 but comma -3. Okay, -3. All right, the next one here, -3 halves comma -2, now becomes -3 halves comma -1. Okay, 0 comma 0 now becomes 0 comma 1. All right, and then etc. etc. Now I can start picking up the pace here. 3 comma 2 now become 3 comma 3. All right, and now it's 9 comma 5 for the next points, and then the last point here, 21 comma 6 now becomes 21 comma 7. These are our final guiding points on the final descendant function g of x. Okay, g of x equals minus f of -2 f of 1/3 x plus 1 plus 1. All right, so let's get to it. Now I'm going to swing over to decimals right here. This is the graph of the original parent function with these being the guiding points listed here. All right, so now these are the guiding points, the transform guiding points. Those are here. All right, and let's say at this zoom level, I didn't have all of those points displayed, so now I just have to adjust the zoom a little bit. Okay, so now we have all 7 of those guiding points of the final step right here being displayed here in blue. And now for better the viewing right here, I'm going to show the point right here. So let's double check right here. So that point right here is 21 comma 7, which agrees with our the final point on the table of values. We have another point at 9 comma 5 from our table. We had another point at 3 comma 3 on our table. We had another point at 0 comma 1 on our table. We had a point at -1.5 comma -1 on our table. This point right here is the same as -3 halves comma -1. The next point here is at -9/4 right here, which is in decimals -2.25. The next one here is at -21 over 8 right there. All right, and so now with the 7 points here, we're going to go ahead and sketch the graph. All right, so now here's the graph of my function from the left to the right. That's how it looks. All right. And that is now in complete view. The graph of this right here is the graph of -2 times log base 0.5 of 1/3 x plus 1 plus 1. This is the graph right here. All right. All right, so example 5 that I brought in was not only intended to show you that all of the elementary transformations we have learned from our past learning will all apply here to this function of a logarithm function. So that was not the only intention, to show you that all transformations apply here to any logarithm function. But I have, aside from that, I would like to underline another important details, another important understanding that I want to start out with looking at the transformation of a graph so that you can start realizing something. Okay, and then from there I want to underline another the important property right there, important understanding. So What is that I'm trying to point out right here? So now, if we're looking back at that first part A of that example 5 right here, the function we had there was, so I mistakenly used f of x in that problem, but later on in that example, I changed that to g of x. So let's call that g of x, okay? So g of x here is the function, the one that we graphed. And of course, here I'm not going to repeat all of the transformation steps like that. But g of x in our example 5 part A, okay? So example 5 part A that we have done earlier. So g of f was 3 times the log base 2 of minus 2x plus 6. And then let's say we had and then subtract a constant 1 like that. So this was our g of f, g of x. We recognize, so all the reasoning was there back in example 5, okay? So along the way, as a part of the process right there, we recognize that there was this g of x here came out as a descendant function from a parent function. So I made my argument in example 5 that g of x came out as a descendant from the parent function being, so the parent function that I recognized here, that I pointed out how we recognized, is that the parent function here was f of x equals a log base 2. So we got log base 2 here of a minus 2x plus 6, but the parent function was a log base 2 of x. All right, so the parent function was a log base 2 of x, and then yes, this g of x came out as a sequence of all 4 elementary transformations that applied. There were horizontal scaling, and then horizontal shifting, and then vertical scaling, and then vertical shifting, all of that. And I worked that through carefully through a table right there, so that we can sketch down all the guiding points from the beginning, the original parent function, and then we applied the transformations on that. Okay, so that was the work for how we were doing, how we revealed our understanding of transformations, and that we apply that into this new family of functions, the logarithmic functions. But then again, like back at what I was saying earlier, that was not the only intention that I brought in this example. Now I want to pinpoint another detail right here. So allow me to swing over to the other board, and also I'm gonna turn on my graph at the computer station right there. Okay, so let's tackle down before I talked about this descendant function g of x right from example 5 part A right there. Before I talk a little more about the graph of this, let's one more time look at the graph of the log base 2 of x like that. So now on my computer station, log base 2 of x, and this is currently now for that example 5a right there, then log base 2 of x was in place of the parent function, and the graph was this shape right here. And we've learned previously that this function here has an x-intercept right at 1, 0. And this function stays completely to the right-hand side. So whatever the information I'm saying right now is not new. The graph stays completely to the right-hand side of the y-axis, where I also stated clearly that this graph and any logarithm function has a vertical asymptote. So this specific function here, log base 2 of x, has a vertical asymptote right at x equals 0, which is this vertical y-axis right here. Okay, and then the graph stays completely to the right-hand side of that. All right, so now on the board here, the picture of the graph has a consistent explanation with the way how we understood about the function at this point. So I also discussed earlier in this lecture that generally for any logarithmic function, the simple one, the logarithmic log base a of x right here, for any function like that, okay, for any logarithmic function, the simple logarithmic function like this, log to a given base, log base a of an x, simply just that, then the domain is of any simple logarithmic function is that the domain has to be in the interval anywhere between 0 and positive infinity. Or another way of saying the input value for our function here, for any for any simple logarithmic function, has to be a value x input that's positive. So again, this is not new information. We've seen this earlier in the lecture over here. And that is making it consistent with the fact that and now I don't even want to swing back to the computer station there. Our specific graph in example 5, the parent function, where it was log base 2 of x, this domain understanding is perfectly consistent with the fact that our graph stays completely to the right hand side, and we have a vertical asymptote. Okay, we had a vertical asymptote, and it's not just we always have a vertical asymptote for this function, because this function here is one in that family of all the simple logarithmic function. And so vertical asymptote at x equals 0. You see, and the graph stays completely to the right hand side, consistent with this understanding right here that I'm underlining right now. And that's all due to all consistent with the fact that we have learned the domain of any simple logarithmic function like this has to be anywhere between 0 and positive infinity. See, the graph won't even hit the vertical axis here. It won't even hit the y-axis. Okay, and then of course, now this x-intercept here for the basic one like this, for a simple log base 2 of x, it was at 1, 0. 1, 0. But that intercept on the x-axis is not really the main aim that I focus here, but I would like to focus on the fact about the vertical asymptote. So this is the vertical asymptote for the parent function. This is the parent function from our example 5 here. And then it's consistent with what we generally know, that anytime we're looking at a simple logarithmic function, okay, just in this form, this general form, a log base a of x, then that will, according to what we know at this point, it will have a function like that, will have a domain anywhere in between 0 and positive infinity. Okay, or another way of saying x is positive, the input is positive. Okay, and so the graph stays completely to one side, and here specifically the right hand side of the vertical asymptote. The graph stays to one side of the vertical asymptote. Here in this problem, it's to the right hand side. But I started to generalize the idea a little more. The graph of the function stays only on one side of the where we call the vertical asymptote. All right, so let's not beat around the bush anymore. This is everything we knew, or everything we know about the parent function from example 5a. This is everything we know about the parent function from example 5a. Okay, and so now let's head over to the other board one more time. All right, so I've talked about everything we knew as far as the vertical asymptote for this parent function. Now let me clear that away. The parent function here is clearly log base 2 of x. Maybe let me just note that here, just to retain that note. So the parent function was f of x being the log base 2 of x. So now let's look at the graph of this g of x, the descendant function, which came out after we apply an entire sequence of transformations. There were horizontal scaling, there were horizontal shifting, there were vertical scaling, and then vertical shifting. 4 elementary transformations apply to eventually produce the graph that we have already seen at the end of example 5a right here. But let's have a look one more time right there. And then at this point, before I bring up the graph, I want you to bring the vertical asymptote characteristics from the parent function and see how it has, and see if this descendant function has that similar characteristic in it. Okay, it's a descendant function. It came from a parent, so the parent had a vertical asymptote. This descendant one should have one as well. That's the idea. But will it be at the exact same spot, or it's going to be different? We're going to find out. Okay, and so now I'm on my graphing space right here. The graph that's currently showing here is the graph for the parent function in red color right here. Log base 2 of x. Log base 2 of x. It had this intercept on the x-axis, right, at 1, 0, but really that's not the one I would like to focus. The vertical asymptote is here, right, at the y-axis, and I've had all of that explanation very carefully just now. Okay, and the graph stays, for this parent function, the graph stays to the right-hand side, of the vertical asymptote right here, because that's making it consistent with what we're understanding, that the domain for this function, log base 2 of x has to be, for all the input, for all the x values, greater than 0. Okay, greater than 0. But now generally I want to start pushing anyone learning the lesson here into that understanding that a little more generally, the graph for a logarithm, for this logarithm, or generally the graph for a logarithmic function stays to one side of wherever its vertical asymptote is. Okay, so once again, that's everything I mentioned about the log base 2 of x, the parent function of our g of x on the board earlier. And so now, this is the graph for g of x in blue. Okay. Now, sadly, at this current zoom level, it's not showing much of the entire picture. Allow me to put it in a far zoom right here. I'm going to zoom it out, and maybe the zooming is going to even make some of the grids disappear right here. But this is the graph for the graph in blue here. Now we have a much better picture. The graph in blue here is the graph for our function 3 times log base 2 of the minus 2x plus 6. In parentheses, minus 1. This is the graph right here. So this graph in blue, okay, this graph in blue right here, that is the graph for our function, the one in blue that you're currently seeing. All right, so let's look for that. As I said earlier, before we got into that, looking at the graph here, let's look for whether this descendant function still carries some of the characteristics from its parent. We want to see if this child, this descendant, still has some of its characteristics from its parent. Okay, any one of us here, we carry some traits from our earlier ancestors, from our earlier generations. Okay, most closest, our parents. All right, and so the same idea here. 4 transformations was applied here, but let's see if this descendant still has some of the traits or some of the characteristics from its parent function. And that's the idea right there. Okay, and so I specifically want to focus on the vertical asymptote. We are so clear that this function f of x, the parent's function, the log base 2 of x, stays completely to the right-hand side of the vertical asymptote at, the vertical asymptote for this function was at x equals 0. And then this graph here stays completely to the right-hand side of this y-axis. And we're still seeing that on the graph right here, even though it appears to be just a little corner, because I would like to now focus more on the blue graph. All right, so now if we're looking a little closer at the blue graph, we do see some asymptotic nature. Just the picture right now, I didn't even put in the vertical asymptote yet. Okay, but there it does look like, it does appear on the graph right there that we do have some kind of vertical asymptote. So seems like, so everything I'm according to what we see right now, allow me to describe what we are seeing. So looks like, right? It looks like, because right now I'm not sure, it's just everything that meets our eye, I'm just documenting it. So it looks like, okay, it looks like there's a VA, vertical asymptote. Because if we're looking at the shape of the graph in blue right there, now this time the graph points completely in the opposite, the one in blue here points in the opposite direction with the one in red. Okay, no worry. So the shape, the direction is explained through the transformations that we've done in example 5. Let's be done with that, okay? But now, yes, provided the shape is pointing in the opposite way, but as far as the asymptotic behavior, it still looks like there's a VA right here. Okay, it still looks like there's a VA right here. For that blue, let's focus on the blue. All right, so now I'm going to one more time swing over to the computer station. All right, so with the computer station right now, with the graphing utility being brought on screen right here. Now let me hide away the original parent function now. this graph in blue right here does, as I mentioned earlier, does appear to have a vertical asymptote. Okay, so where can that be? So right now, allow me to just point it out, and then I will put in more explanation of what explains it. Okay, so it looks like this graph here, and the grid, see, the grid is not doing a good job here in terms of showing the vertical asymptotes any longer, because it had, the grid is hiding away some subgrids right here. All right, but we have a vertical asymptote right at this vertical line right here, and this line, ladies and gentlemen, you see the graph in blue, keep getting closer, but never cross that line in black dotted ink right there, and never cross to go to the right hand side. So the graph in blue here stays completely on one side. So there is a vertical asymptote. So now back on my board, it's not only that it looks like there's a VA, clearly now there is a VA. So as a thought process, see, it looked like from what we estimated in the graph, it looks like there's a VA. But now I put it in there and I'm confirming, we confirmed that there's a VA. Okay? Now that it's confirmed. So as a learning process, that's how I see it. There's a VA now. But where exactly is that? Okay, where exactly is that? Now, so allow me to, in my experience, allow me to point it out with my experience right here. The VA is at that vertical line, x equals 3. The VA is at x equals 3. The VA is at x equals 3. Okay? So I will get further into how I can explain this. Okay, but right now, yes, now we confirm there's a VA. Just like the parent function had a VA. The VA was at x equals 0. Now this descendant function also has a VA. Just no longer at x equals 0, but it at x equals 3. It's a vertical line right there. For the parent function, the graph stays completely to the right-hand side of the VA. Here, our graph for this descendant function stays completely to the left-hand side of the VA. But still generally, I want to emphasize that the graph stays completely on one side, only on one side of the VA. Okay, so that's one observation. Another observation, the graph. Okay, the graph stays, and of course I mean the graph of g of x. The graph stays only, okay, on the left. Okay, on the left of the VA. Okay, vertical asymptote. All right, so now we will get closer into this and see why it's like that. You see why it's like that. All right, so, but now, like I said earlier, generally, so here specifically for this graph, for this function, the graph stays completely to the left-hand side of the VA. But more generally, I want to emphasize what I was saying earlier. The graph stays on one side, only stayed on one side. The graph here stays on one side of the vertical asymptote at x equals 0. Specifically, it was the right-hand side. Here, the graph stays on one side of the VA, but specifically at on the left of the VA. Okay, and we want to get into all of that explanation. Okay, so now on this board of mine, allow me to bring back a little further about example 5 that we've done. Example 5 focused on the transformations. So let's for now use the transformation to explain why the graph stays generally the graph stays on one side of the vertical asymptote. Let's use our understanding of the transformation to explain why the graph has a vertical asymptote at x equals 3. That's the first thing. And further, why it has to be to the left-hand side. All right, so the parent function was f of x equals log base 2 of x. Needless to keep talking further about that. G of x throughout our example 5 was recognized as 3 times f of x. I mean 3 times f of minus 2x plus 6. So the minus 2x plus 6, that linear expression, goes inside of our parent function as the input argument, and then minus 1. So that's why throughout example 5, part A, I was explaining this coefficient inside of our log function, inside of our parent function, was responsible for the horizontal scale, okay? Stretch or compress or even flipped. The negative sign was explained for the flipped. And then that value right here, we have to do some further trick, but it's responsible for the horizontal shifting, bringing left, bringing right. And this is what explains for why we have a vertical asymptote other than the ones here for the original parents function. The vertical asymptote here in the original parents function is at x equals 0. But see, again, the VA for this descendant function was at x equals 3. See, it looks like it's got shifted away, horizontally shifted away. See, it changed to a different x value. All right, so some explanation about that. So now let's get into that table. We don't have to get to the whole table of all guiding points, but we only need to use a table to point out, to pinpoint why we have a shift, okay, how we have a change for the VA, the position of the VA on the x-axis. And we want to also explain why the graph stays to the left-hand side of the VA instead of the right-hand side, like the beginning one right here. So let's use transformation to explain that. Okay, so, and then by the way, this f of minus 2x plus 6, that linear expression inside of the function, it's always better. And we've learned at this point, we've done quite a few problems already about how we apply the transformations. It's always better that we factor the linear expression inside our function here into the into the factor form where we factor out the coefficient minus 2 here. So a better way of writing this, g of x is 3 times f of, okay, minus 2 factored out. And then I'm looking at x minus 3 and then minus 1. This is really making it so clear. This is really making it so clear that this is a horizontal, we have horizontal shift right there, and that's responsible for where we're shifting. So the VA will get shifted. The vertical asymptote will also get shifted. And then this coefficient here, now factored out, is responsible for the horizontal scaling. Okay, and then of course reflection included. Okay, the reflection can also be included as part of that because we noticed, we spotted a negative coefficient here. All right, so that's why in that way, now allow me to just delete these extra notes right here. That's just to remind you what would be happening. So as far as the table, okay, we don't need to build the entire table with all rows in there. Let's just point out a few things. And you see, I only focused on the transformations that happen on the x-axis right now. So for the beginning function, okay, the VA is happened at x equals 3. This is VA right here. The VA happens at x equals 3. All right, it's x values, and that's why I only need to focus on things that happens on the horizontal direction, on the horizontal axis. Okay, all of those transformations that happen on the horizontal axis like that. So in the next column, f of minus 2x. F of minus 2x. So recall from our understanding, we're going to divide every x value. We're going to divide every x value by, and I just now noticed, this is supposedly 0. I'm talking about the beginning, the original VA. Okay? So now for our function f of x, okay, the VA originally was at x equals 0. And this is now the reason why you can see VA is measured, is indicated by x value. It's located on the horizontal axis. This is the reason why, and we would like to explain, why the graph is on the left or to the right of the VA right there. So everything is about the x values. That's why I only need to focus on those transformations that happen on the horizontal axis right there. That's the idea. All right. So now in this way right here, then now from the beginning parents function, the VA was located at x equals 0 for x value. So now I'm going to produce a column, just like how we were doing the transformation. I'm going to produce a column for f of minus 2x. Okay, see how this, we want to see how doing this will change our position, our location of the VA. All right, and then by the way, so if this is, or maybe I can get to that a little later, but so now recall from our understanding, if we multiply, if we looking at f of an a times x right here, then we're gonna divide, we're gonna multiply every x values by 1 over minus 2. Okay, so 1 over m right here is going to be 1 over minus 2, and then we're gonna multiply, which is a negative 1/2 right here. We're gonna multiply every x values by negative 1/2. Multiply every x value by negative 1/2, and so that means if it was this function, the VA will be changed. To this function right here specifically. Will be changed to x equals 0 as well, because negative 1/2 but multiply with the x coordinates, the x values of the original of the preceding step, the x value of the VA from the preceding step is a 0. Okay, because negative 1/2 times 0 is a 0. So our VA is still 0 here. All right, so that's what explains. But now, after that step, this is the vertical, this is the horizontal scaling. So in the next step, I'm going to produce f of minus 2 times x minus 3. And this is now, again, this is in what we're understanding, this is responsible for the horizontal shifting, the shifting that happens on the horizontal axis like that. And so now this value, the negative sign is indicating there's a horizontal shifting, but the value itself is a positive 3. All right, the value itself is a positive 3. And so now we're going to add every x value, including the x values that explain where our vertical asymptote is at. So we're going to add every x value by this value right here, this constant. And so that means now it's our VA here. That's why this is what explained that our VA is shift to 3. Because, see, 0 was the preceding step. The 0 was the x value of our VA in the preceding step, in the very preceding step. And now when we add 3 to every x value, including the x value of the VA right there, we ended up with 3. X equals 3. That's what explains for why our VA is changed to, from originally x equals 0. Now our VA is relocated to x equals 3 right there. All right, so that's what happened to the x-axis. That's what happened to the VA. And then think about it now as a process right here. I got in this a little bit, and then I kind of roll back, and now I want to say for this step right here, when it was this original parents function, the idea about the domain right here. Okay, the idea about the domain is that the domain is all the x values greater than 0. And then when it came to this step right here, due to that negative sign, and I wrote it down earlier, and just now I had to erase it, but having a negative 2 coefficient inside of of our function here means we're going to multiply every x values with minus 1/2. Okay, this is 1 over m right here. So we're going to multiply every x values with negative 1/2. But see, multiplying, if x is greater than 0 for the domain, then multiplying every x values by negative sign is going to make this function right here, this function is going to have domain. Think about x greater than 0, but now if I multiply negative 1/2, okay, to x right here, then that's going to make it less than 0. That's going to make it less than 0. That's indicating that now for this function right here, the domain has to be some x value that's less than 0, because we multiply by a negative number. All right, I did that little work earlier, and then I erased it. Think about an inequality. We multiply a negative number to both sides, so it results in the inequality be flipped in direction. And then that x here is not the same x as that beginning. It's just the x for whatever this function is, but now the x has to be a negative number. So this is the turning point where it switched the graph to the left-hand side instead of the usual right-hand side of the parent function. The parent function originally had the graph appear completely to the right-hand side of the VA. See, the VA is at x equals 0, but now to the right-hand side, x greater than 0. But now, at least for this function now, f of minus 2x, the first transformation applied right there, then it caused the domain to flip the other way due to that negative sign. That's how I had it. All right, and then now we shift by 3 right there. So we add every value by 3. So think about this final version right here, f of minus 2 times x minus 3. Think about the domain right here again. Now we're going to add every x value by 3. So think about this preceding step. X less than 0, but I'm going to add 3. Okay, I'm going to add 3. So I'm going to consequently end up with really x is less than, okay, x plus 3 is less than 3. Okay, but the x plus 3 is the updated domain for this part right here. So now in the end, see every x value, that's why now x is the domain for this function here has to be less than 3. Less than 3 because I add 3 to that 0, I add 3 to that 0 and ended up with 3 right there. And this x again is not really the same, it's not the same as the x value in the preceding step. This x is after we added 3 from the preceding x right there. All right, so that's what explains why our domain for this function here, the descendant function, is less than 3, or explaining that the graph stays completely to the left instead of the right-hand side compared to its original parent function right there. All right, and so now we use the transformation to explain. But it took a lot. It really took a lot, and we got to tear down the table, and it took so much to explain. Right there. And we definitely don't want to repeat all of this process. I mean, this is a process maybe for a professor who has been years of experience, right? And then trying to give that explanation out to the students for the student to understand. But then as far as letting the student do the work, this is not an effective way for a starter, for a student who is starting to get into this work right here. So how about let me point out another way right here that's hopefully easier. Okay, so that was the explanation through the transformation. And as I pointed out earlier, it has a weakness. It takes a lot. It will take a lot to explain. Especially, see, it took so much to explain why the vertical asymptote is shifted to the new location, and then it also took so much to explain why the domain is flipped the other way instead of to the right-hand side. All right, and so now that's just for anyone to understand. But then, if anyone learning from in the course here really had to do it, there's a better way of doing that. And this is also a formal understanding as well. Okay, so think about, all right, so our g of x here, let's really write it down this time. This g of x was defined as 3 times the log base 2 of the minus 2x plus 6 right there and minus 1. Now, we want to come up with a mathematical explanation instead of the graphical approach like I've had earlier with so much transformation applied in it, and it's going to lead into some headache for anyone. So this time let's use some actual math right here. It does take some thought process as well, but it's, at least in my personal understanding, it's not as painful as the other approach like that. So the coefficient and the constant term here are not really important. That's not the one that deciding the domain. These are not the deciding domain. So you can nail it down. You can take my word on that. Okay, and when your math become more advanced, you can also explain that on your own why these two are not the explaining factor. These two are not the explaining factors of why our domain changed. So let's cross them out, and I cross them out with red ink. Those are not the determining factors that changes your domain. What changes your domain is here. This is really what changes your domain. This is what changes. All right, that part right here is what changes your domain. So why is that? Because see, think about it this way. I have made this argument earlier. For any logarithm base 2, I mean, doesn't have to be base 2 for any base, logarithm of x. Okay, we agreed already that the x here has to be positive. The x values, the input has to be positive. But then I also gave that explanation. I also gave the explanation earlier in this lecture. In case anyone have not come across my lesson, my separate lesson about the properties of log, then I also have a different interpretation. I mean, a different explanation of why the inputs of a logarithm need to be positive right here. So think about it. Why did x need to be positive? Why did the inputs for a simple logarithm like this need to be positive? That was simply because think about the outputs right here. If this function here comes out with an output, then this now has for us an equation there, and that equation here is currently in logarithmic form. So in exponential form, then we're looking at e to the y equals x. This is exponential form. Same equation, but this is exponential form. This is logarithmic form. We've learned this since our beginning, since our introduction to logarithm. Anytime we're having an equation that expresses relationship logarithmic in logarithmic form right here, then there's always an equivalent exponential form of that relationship. Okay, so let's look at right here. See, x, if our log base 2, and this shouldn't be e, this is just 2 to the y, it's the same base, forget. All right, so but again, back to what I said. If our x value is a value satisfying log base 2 of x equals y, then it has to be equivalent to 2 to the y equals x. But look at this right here. I made my argument that 2 to the y as an exponential function will never be negative. Okay, never even be 0. So 2 to the y, it's because 2 to the y is always positive. We've learned this in our exponential functions, in our learning about the exponential function. And that consequently implies that the x values here, which is the same as this input, this argument of the log. Okay, so this x here has to always be positive. That's the explanation why for any logarithm function, the input variable has to be positive. All right, so that was for the case where it's just one simple x variable being inside of a logarithm. And then all of a sudden it produces a bigger challenge when the input is like this. The argument is not just one, see, the input variable is just this x, but the x is multiplied with -2 and then plus 6. See, life is a lot more complicated now with this expression instead of an ordinary input like that one. Okay, but now I can use the exact same arguments. To explain. Think about just that part right there. Just that log base 2 of the entire minus 2x plus 6. All I need anyone to follow with me is that for the rest of this explanation, we always going to keep this whole thing here as one package. Minus 2x plus 6 as one package. You don't have to focus particularly to just the x only. So yes, the x is the input. The value of the x is the input, but together the whole minus 2x plus 6 is an argument. It's the arguments where log base 2 here applies on. Log base 2 here is not applying only on the x, but the log base 2 operation here applies on the entire minus 2x plus 6. So think about that. If this comes out to be an output value y, a different y maybe, okay? Y, lowercase y, capital letter y, doesn't matter, but this is logarithmic form, okay? Logarithmic form of an equation. And so we can do the equivalent and very similar thing. We can have base 2 raised to the y has to equal the minus 2x plus 6. See, that's why I was asking anyone earlier to look at the whole thing here as one entire package. So now in the way how, and we've also had examples that we specifically applied the skills when we were learning about the introduction to logarithm. So anyone viewing this lesson here should not be shocked about what I'm doing here. So from a logarithmic form of an equation, I turn that into an equivalent exponential form. And so that's why I also keep asking my viewers, my students who are viewing this lesson to see this as one package, because that one package here, the whole minus 2x plus 6 as one package, as one expression, must equal 2 to the y. The whole package here must equal 2 to the y. But again, 2 to the y now is seen as an exponential function. Okay, so 2 to the y is always positive regardless of whatever y value is. 2 to the y has to always be positive. It's just the way how an exponential function is. So if you're not sure about what I'm saying here, you can review my earlier lessons about the exponential function. But now 2 to the y is always positive, no matter what y value that is. And so in that way, see, but 2 to the y equals this expression. So now in that argument, I can take it further that the minus 2x plus 6, the whole package, the entire argument. That's why I somewhere here and there prior to this lesson, I also use the term an argument. So logarithm is an operation, and then whatever logarithm, whatever quantity, not necessarily one single number, whatever quantity that logarithm applies to, that is called an argument. So an argument here is sometimes a lot more than just simply an input value. So as far as being a function, the input is the x value here, but the whole thing here is the argument of your logarithm. That's how I see it. So now back to my point. So I made that argument earlier that now this minus 2x plus 6 has to be for sure greater than 0. This minus 2x plus 6 must be greater than 0 because it's the argument of your logarithm. It's the part where your logarithm applies to. So the whole minus 2x plus 6 must be ensured to be above 0. That's the starting key right there. So all of this here was explanation that leads to, so now generally anytime you're looking at logarithm, base 2, base 3, base e, base 10, base whatever base, but logarithm of an expression, we can always generally hammer down right there, that's take the whole logarithm, take the whole arguments of your logarithm, make it greater than 0. This is always what we want to ensure. This is always what we want to ensure. So we have to ensure the minus 2x greater than minus 2x plus 6 greater than 0. And so now in order to ensure this, all of a sudden we realize we have an inequality to solve for. So I can subtract 6 from both sides, okay? And to end up with a minus 2x greater than negative 6. Okay? And then I'm going to divide both sides by negative 2. I'm going to divide because we want to solve for x. So we want to divide both sides by negative 2, and doing that, it will flip our inequality. All right? And so now I'm going to use this larger space right here. So the minus 2x being greater than negative 6 at this point, dividing both sides by negative 2, okay, will result in my next step right here. The inequality symbol will flip direction. Minus 2 cancel with minus 2 leaves me just x, but the negative 6 divided by negative 2 is 3. This is, ladies and gentlemen, this is the reason why, this is what explains why the graph stays completely to the left-hand side of x equals 3. Now on the graph, x equals 3 is right at our vertical asymptote. And our graph stays completely to the left-hand side of x equals 3. Or in other words, this is indicating that x has to be less than 3 right here. In order for this function, the g of x equals to 3 times log base 2 of minus 2x plus 6 minus 1. In order for this function to be defined, okay, then we can only pick input x values being anywhere less than 2. All right. And so in that way, that's what explains, mathematically, that's what explains for the domain of this function. So now we've gone a long journey enough. What I wrote down earlier, that solving inequality I've done earlier, explains why the domain for this function, the domain for this g of x is where x is less than 3. That's one way of how I see that. And then that's equivalent to, so in this way right here, it's the same as in interval notation, it's the same as the interval anywhere between minus infinity and 3, okay, and completely an open interval. All right, so this mathematical explanation also takes some process to explain, but then long story short, we can take things down into some, we can simplifying all of that talks, all of that discussion into one thing. Anytime that you are looking at, anytime you're having a function, now we don't even have to worry about really is it a logarithmic function or not, but anytime we're looking at applying a logarithm on an expression, on a function other than just a simple x right here, then the whole function here may be a real logarithmic function or maybe not. It's just, but as long as you have a logarithm involved, we always have to ensure the generality I want to point out now is we always have to ensure. We always ensure the expression, okay, or you can understand that as the argument, the expression inside of a log, okay, to be positive. That's one thing we always have to ensure, and that's what leads us to getting the proper domain. And so earlier I was making that argument. I had to ensure this to be positive, greater than 0, the whole minus 2x plus 6 to be greater than 0. And then I had leading explanation that led into why we have to ensure that. Okay, and then because we need to ensure this entire expression inside the logarithm must be positive. That's why it led to solving the inequality work, and then it came, for this particular problem, it came down to x less than 3. All right, and so this is the way how we can mathematically explain that about the domain on any function, not necessarily just logarithmic function, but any function that involves a logarithm. Any function that involves logarithm. Okay, and so now we just always, anytime we have a function, and like I said, doesn't necessarily have to be a logarithmic function, but as long as there's a logarithm involved right there, then we always going to have to ensure the expression inside of a log to be positive. Okay, and so we came up with a different way to explain why the domain for this function is entirely to the left-hand side of the vertical asymptote. X equals 3 was a vertical asymptote, and then we came up with a mathematical way to explain why the function here stays completely to the left-hand side of the vertical asymptote. And then another language of that, the domain is anywhere in between negative infinity and 3. So let's see if we can reuse this understanding right here. If we can reuse this and apply this general understanding on our part B of the example 5. So I don't want to use the transformations to explain for all of that nature anymore. Okay, let's just look at example 5b, but now with this understanding, the process is going to be a lot faster. Okay, so now on this board of mine, let's look back at part B of example 5 right here. All right. So we were given that descendant function g of x to be a minus 2 times log base 0.5. Okay, log base 0.5 of the 1/3 x plus 1. Okay, and then add 1. Minus 2 times log base 0.5 of 1/3 x plus 1, and then after the parentheses plus 1 right here. Okay, and then yes, in our work of example 5b, like of example 5 part B, we already recognized, and then here needless to keep getting back to that earlier example. So parent function here was f of x being a log base 0.5 of x, just that simple logarithmic function. Okay, and so now we want to look at this function. We want to once again swing over to the computer station right there, look at the graph of the parents function and look at the graph of this logarithmic function here. Okay, and then we want to find out how this descendant function still has some of its characteristics from its parents. Okay. All right, so this is the graph of our log base 0.5 of x. Log base 0.5 of x. This is the graph for it. And so this graph has a vertical asymptote right on the x-axis, and it appears to the right-hand side of the x-axis. Having an intercept on the x-axis here is not too important. But this graph, so this graph has a vertical asymptote right on the y-axis right here, which is the line x equals 0. Okay, the graph appears completely to the right-hand side of the y-axis here, or another way of calling that, appears to the right-hand side of the vertical asymptote. The graph has an intercept right on the x-axis here at 1, 0, but that point of the intercept is not important. So now the VA here is at x equals 0, or the y-axis, and then the graph stays to the right-hand side. So that indicates the domain of this function here, log base 0.5 of x, is anywhere x greater than 0. That's the domain. And then we have a vertical asymptote at x equals 0. Let's now write it down. So we have a VA. We have a VA at x equals 0, the y-axis. And then the domain here for this function. All right, the domain is x being greater than 0 to the right-hand side of the vertical asymptote. Okay, and we saw that on a picture earlier. And so now let's look at the graph of the descendant function g of x, minus 2 times the log base 0.5 of 1/3 x plus 1, and then after the parentheses plus 1. So this is the graph of our function right here. Right. So this is the graph of our function g of x. So according to the picture over here, and right now for this problem we have the grid can still be displayed right here, can still be quite visible. Okay. So the graph in blue, the graph in red here was the graph for our parents function, and this graph in blue here now is the graph for the descendant function. So the graph in blue there is the graph for the descendant function. So it looks like, again, in the thought process, it looks like, according to the graph, it looks like there is a vertical asymptote spotted. So where exactly is that? Let's swing over to the board, to the graphing space, and look at that. So now I'm going to put it in. All right, and the grid, in this case right here, the grid is making it clear enough. But then let's just put it in right there. The vertical asymptote, just now I put in is that x equals -3. All right, x equals -3. So it looks like the graph in blue here has a vertical asymptote, and clearly it's just not going to cross through that vertical line to go jump to the left-hand side. Okay, to jump to the other side. So this graph here in blue has clearly a vertical asymptote at x equals -3, and then it stays to the right-hand side of this graph of this vertical asymptote. Okay, so that explains that. So from the picture, we can see that the domain of this function here is anywhere to the right-hand side, of x equals -3, or mathematically x greater than -3. All right, so let's put it all together. We recognize there's a VA for this graph right here. There's a VA at x equals -3, and the graph itself suggested a domain that x is greater than -3. X is greater than -3. But so why is that? So let's apply what we're understanding. Let's apply our understanding that I brought out earlier into explaining this. But definitely we don't want to explain things using the transformations on a graph any longer, because it takes way too much thinking. There are way too much steps. Okay. So now we want to explain why we have a VA at x equals -3, and why the domain is to the left-hand side. To the right-hand side of that VA right there. And it's just all in one step. All right. And so now, again, from the earlier explanation I've made right here, this is a log. This is a function where log is involved. I don't even need anyone viewing the lesson to see this as a logarithmic function or not. that's not the important part, but as long as you see a logarithm involved in your entire function, as long as there's a logarithm involved, take my word for that. As long as there's a logarithm operation involved in your entire function, then we're going to tackle down right into that entire arguments of your logarithm. So your function here has log involved in a way that we take log base 0.5 of this whole argument, and then after that output we're going to multiply with -2, and then we're going to add 1 afterward. That's why I said log involved, and without worrying about whether it's a logarithmic function or not. That's not even important. So, but now as long as we have a logarithm involved here, then we have to tackle down right into that arguments, that part that we place inside of the log. Okay, we're going to tackle down right there. So now I underline that with the red ink. Okay, we want to always ensure that this quantity, is greater than 0. Okay. So we want to ensure. So right from that expression that I underlined in red ink, that we want to ensure that the 1/3 x plus 1 is greater than 0. That's what eventually will lead to our proper domain for this entire function. And I still don't need to call this a logarithmic function or not. But as long it's already a function and it has log involved. But this is the way to get to the proper domain of this entire function. And that's the idea right there. All right, so now I just want to ensure that the entire argument is 1/3 x plus 1 is greater than 0. And so now in that way, here's what I'm seeing. Yes, we can subtract 1 from both sides to produce a 1/3 x is greater than -1. It's a simple linear inequality to solve like that. And now I can multiply both sides, and notice the number we are about to multiply on both sides here is a positive number. And so I can just simply, and what I meant earlier is that it will not change the direction of our inequality. So now multiplying 3 to both sides, right? 3 here and multiply 3 there, it's going to produce for us x greater than -3. Now after successfully solving for the inequality, that is our domain. Okay, ladies and gentlemen, this is our domain of this function where a logarithm is involved. Yes, this function is officially a logarithmic function, but as far as more than just a logarithmic function, then anytime there is a logarithm involved in your function, then we just have to tackle down and ensure the argument inside of the log has to be positive. That's my point. I always want to emphasize that. Okay, and so now doing this right here in this function, it only depends on that. So our domain is now ready to be concluded. So this function has domain anywhere x greater than -3, or in interval notation, anywhere between -3 and positive infinity. Interval notation or inequality notation. That's the domain. And now once we have found the domain, then now just think about that line right here. Hey, so when x equals -3, of course, x cannot equal -3, but that's where it's asymptotic, right? That's where it's asymptotic. And so now we can just simply change the inequality to equal signs to obtain x equals -3, and now I'm saying we have a vertical asymptote at x equals -3. That's how we find the domain and also trace down the vertical asymptote. The vertical asymptote for any function with a logarithm expression involved there. Not only a logarithmic function. All right, and so now all of a sudden what I've done here introduces a common method to find domain and as well as vertical asymptotes for any functions as long as there's a logarithm involved in your function. Not only just logarithmic function like that. All right. So now in that way, now anyone viewing the lesson here is ready for heading into another example, example 6 right here. All right, so now for example 6. Let's get straight into the point right here. We want to find the domain. Find the domain, okay, of the given function. All right, and you can notice already I did not even call the function here a logarithm function, because any function you're about given here in this example, there will be log involved, okay? But some of those will be logarithmic function, some of those will not, okay? And so now, part A. So you don't need to worry whether it's a logarithmic function or not, but it's a function that has logarithm involved. So our function f of x, how about f of x equals a natural log of a 3x minus 5. Yes, admittedly this function has this function is a logarithmic function, because according to our definition that we have extended earlier in the lecture, then yes, this truly is a logarithmic function, but that's not important. What I see here generally, this is a function where it has a logarithm involved, a function that operates with a logarithm, a function that has a logarithm involved. And the logarithm here is a log base e that applies on the expression on the arguments 3x minus 5. So x, just x, is the inputs, admittedly, but the entire 3x minus 5 as an expression, entire 3x minus 5 as an expression here is the whole argument, the whole expression inside of our log, where our logarithm operation applies on that whole 3x minus 5. And so now the example here, the instruction of this example is stating that we want to find the domain of this given function. See, so regardless of being a logarithmic function or not, we're gonna tackle down right at the expression inside the log. We want to ensure that this expression has to always be positive. So we want to ensure that 3x minus 5 is positive. That's the first thing we always want to do anytime we're having a logarithm involved in our problem like that. All right. And so now in order to ensure the minus 3x, in order to ensure the 3x minus 5 being positive, then I'm going to have to look for the proper x values, and that's where it leads to the solving work for an inequality. So plus 5 from both sides, right? I'm going to end up with a 3x greater than 5. And then I'm going to divide both sides by 3, and that leads me to x being greater than 5/3. Now, ladies and gentlemen, that's how easy it is to find the domain, because now I'm ready to conclude about that domain. The domain of this particular function, logarithmic function or not important, but as long as there's a logarithm involved, the domain of this entire function has to be, as far as in inequality notation, x is anywhere greater than, strictly greater than 5/3. This is the only way to ensure the entire expression inside a log being positive. That's the argument. So that's one way of writing the domain, but of course, a lot of instructors and professors out there require the students to express the domain, and that's most of the cases in these days. We want to express that in interval notation. So 5/3, comma, positive infinity. That's the domain in interval notation. The domain of the function is anywhere between 5/3 and positive infinity, because only x values in that zone will ensure this expression inside a log to be positive. All right, and then of course, even though the worded instruction of the problem of the example did not ask for this, but you can see that, hey, for this function, for this particular, if you're seeing this as a logarithmic function, yes, it has a VA. So this is just extra note right here, even though the question did not ask for it. The VA, okay, is at x equal 5/3. That's what the VA is, but the question just didn't ask for that. All right, so that's part A. And so now see, it took me a lot to, not as much as the transformations, to explain about how we can mathematically trace down or track down the proper domain for any functions involving log, any function involving log. And it also involved our previous understanding right here in this lecture that about we have to be able to interchangeably write things between an equation in logarithmic form and an equation in exponential form. But that explains all of that reasoning why we have to always ensure the expression inside of a log to be positive. And then from this major understanding that I'm writing, that I wrote it down in red ink right here, we use that as the only key that leads to any domain, or that leads to the domain for any function that involves log. And I'm saying any function that involves log doesn't necessarily just apply to the logarithmic functions only, because to me logarithmic functions still refer to just one specific family with the forms that I indicated earlier, where just anytime you're gonna be for anyone after learning this class right here, you're also gonna advance to other classes, and there will be a lot of functions where there's polynomials coming together with logarithms and coming together with exponentials, with functions like that. Then good luck classifying it. But as long as there's a logarithm involved right there, your function has to, at least the expression inside of that has to be ensured to be positive. All right, and that's the idea right there. So now, once we nail down with this major understanding right here, let's lead that into part B of our example and some further problems in the same example 6 right there. All right. All right, so let's look at part B of our example. Part B of our example. So the function this time is as following: f of x equals natural log of x squared minus 5x plus 6. X squared minus 5x plus 6. All right, and so with a problem like this, see, this function is clearly not a logarithmic function. And this is, I'm starting to, somewhere here and there, I'm starting to point out a couple examples of where I would have something that has log involved, but it's not classified as a logarithmic function. Function like this, for anyone who has the serious intention to go to calculus, you will see this kind of function all over. But function like this, we don't even bother naming it, but we work with these a lot, and they're clearly not logarithmic functions. They have this, it has logarithmic involved. It has logarithm involved, but it's not really a logarithmic function. Simply for the reason, according to that definition I gave earlier, even in the extended version, the expression inside needs to be a linear. Look at this. This is not a linear expression. This is a quadratic expression. Okay, and so now, but see, I brought in this particular problem to really emphasize what we nailed down earlier. As long as there's a logarithm involved, we just need to ensure the expression inside the log here to be positive. That's simply what we need to do right there. Because in the end, the whole thing here is a function. Logarithmic or not important. It has logarithm involved. Okay? And so this whole function here will come out with some domain. Will need to exist in some domain. Will be defined only on some domain, and we're gonna find out that domain. But the only way of getting to that domain, we tackle down right here in that inside expression, to that expression inside of our logarithm right here. So we need to ensure again. We need to ensure that the entire x squared minus 5x plus 6 is positive. All right, we need to ensure the entire expression inside of this is being positive. And so now this particular inequality is what's famously known as a polynomial inequality. A polynomial inequality in a sense that one side is 0, the other side is a polynomial. Here is a degree 2 polynomial. Okay, a degree 2 polynomial, and we want to compare that with either a greater than 0 or less than 0. So right here, we want the polynomial on the left to be greater than 0. We want the polynomial on the left here to be positive. So admittedly, anyone who learns about logarithm or exponential function has to already learn about polynomial, and including polynomial inequalities. So allow me to bring back that understanding. But if you're feeling unsure about what I'm doing here, review your learning about the polynomial functions and more specifically the polynomial inequalities. Okay, so for this polynomial inequality, let me just highlight that name right here. This is a polynomial inequality. All right, and you can go ahead and find the lessons on the polynomial, and more specifically the polynomial inequalities, to learn to understand the actual explanation of why I was doing this. So here I can just point out the way how I do. We factor out the left hand side here into x minus 3 and x minus 2. Okay, x minus 3 and x minus 2. And then, so yes, we're going to come up with 2. So now, if that inequality equals 0, we're going to come up with 2 zeros. The left-hand side polynomial here, we'll have 2 zeros. X equals 2 and x equals 3. These are the zeros of our polynomial on the left-hand side. Again, yes, we want to solve for a greater than 0. Okay, but these are the zeros if the polynomial on the left is set equal to 0, was set equal to 0. And now with these two found zeros on the left-hand side polynomials, we're going to construct a sign chart. So the solving inequality work is different on every problem like that. So now I'm gonna put those zeros in increasing order from the left to the right. So 2 is on the left, 3 is on the right. Okay, and we're going to use a sign chart here to check for which interval, because here is an interval where x is less than 2. This is an interval where x is between 2 and 3. Okay, and this last interval on the right-hand side is where x is greater than 3. Okay, and the inequality, and the polynomial on the left-hand side of our inequality is already in factor form right here, x minus 3 times x minus 2. So 2 identical factors here that produce 2 identical zeros. So I'm using these terminologies from your understanding about the polynomials. So you must review your understanding in the polynomials in order to move on with this particular problem like that. Okay, so I'm going to pick a value in the interval x less than 2. So for example, I'm going to pick x equals 3, x equals 1. That's for sure less than 2. It's just a value that we checked right there. And so now if x equals 1 as a value less than 2 right here, then when we substitute x equals 1 into our first factor, we're going to produce a negative factor, because 1 minus 3 is a negative factor. 1 minus 3 is a negative 2, so it's a negative factor. Substituting this x equals 1 into the other factor, okay, it's going to give us another negative factor. So negative factor times a negative factor. Okay, so in this interval, our entire polynomial will turn out being a positive value. Our interval will turn out positive value for any x value. So x value is in this line right here. So for x values less than 2, our interval will be positive. That's why I'm writing that in red ink right here, in that interval less than 2. So for an interval that's between 2 and 3, we can pick, how about x equals 2.5. 2.5 is for sure between 2 and 3. Doesn't even have to be exactly in the middle. Here it just happened that I chose in the middle, but 2.5 minus 3 is going to produce a negative factor because 2.5 is less than 3. So substitute 2.5 into the factor here is going to give me a negative factor. Okay, but 2.5 substituted into this x right here, in this factor right here, it's going to give me a positive factor, because 2.5 is greater than 2. So 2.5 minus 2 is a positive 0.5. So I see that as a positive factor. So negative factor times a positive factor as the entire polynomial here will produce an overall negative polynomial, negative value polynomial for any x value between 2 and 3. Okay, and so in that similar argument, now I can pick, how about x equals 4 here? That's just simply a value to pick and test. Like that, test for the sign. So now when x is equal to 4, it's greater than 3. So the first factor will consequently become a positive factor. Okay, and the next factor, substituting x equals 4 into the next factor, x minus 2, 4 minus 2 is also going to give me a positive factor. Okay, and so now positive factor times a positive factor, it's going to give me a positive polynomial anywhere x greater than 3. So now with this sign chart, now just sketching down all of the intervals where our polynomial is negative and the intervals where our polynomial is positive. Back to this particular problem, we want to ensure the polynomial, which was the expression inside of our logarithm, we want our polynomial to be positive. That means these are the interval of x values. These are the two intervals of the x values where it satisfies the polynomial here positive. So that means now, and this is the reason where, this is the place where, you know, writing your final domain in interval notation is better than the inequality, the notation right there. So we have two separate intervals where the polynomial x squared minus 5x plus 6 appears to be positive. Those are right here. So one of them I found is to be anywhere between minus infinity and 2. That's one of them. And I forgot to write down that this, what we're doing here is a final conclusion about the domain. All right, so now for domain right here, one of them is anywhere between minus infinity and 2. We got one interval. And then another interval here is at between 3 comma positive infinity. And so now but anywhere in one of those two intervals will work. So we put the unions between the two. All right, so we have found our domains right here. Okay, and so this function, I wouldn't even bother indicating about the vertical asymptotes because it's, in the end, it's not really in the family of logarithmic functions. So it's not important to point out where the VA is. Because VAs, I would like to specifically focus VAs anytime we're looking at we're working with a specifically logarithmic function. But this function, I made it clear earlier, right in the beginning, it's not really a logarithmic function. So yes, we can use that generality to find out where the domain of this function is, making the function defined. But we don't need to, we don't have to worry about finding out where the VA of this, where the vertical asymptote of this function is. Okay, that's not important anymore for this particular problem. All right, and that's why I left out the VA in the actual overall the instruction of this problem right there. All right, so that's for this problem. Let's look at another problem here in our same example. All right, so how about part C of the example? Let's look at another function. And so now you can start understanding a little further that in this entire example 6 right here, any of those functions given may or may not be an actual logarithmic function. But as long as there's a logarithm involved right there, then your function must be, we must define the domain of the function according to that understanding I've highlighted earlier. So the domain of any function where logs involved, we have to always tackle down and ensure that the expressions inside a log to be positive. That's the big understanding right there. All right. So now the function I want to introduce in this part C of the example, how about f of x equals natural log of x minus 2. Well, clearly this one looks logarithmic function because the expression is linear inside. But now I'm going to add another term, okay, being another logarithm term right there. Natural log of x minus 3. All right, so all of a sudden we fall out of the family, of that family. This function does not belong to the logarithmic function families. It has logarithm involved. 2 logarithm terms here. The reason I keep spelling this out loud, I keep yelling this out loud, is that it could be the same function, it could be the same problem. I could have turned that into a log base 10, and this is a natural log, so it's just 2 log terms and completely 2 different bases as well. Unfortunately, that's no longer a logarithmic function. It's just a function. It's just a function. The rule has multiple logarithms involved. That's how I see it. Okay? So now 2 logarithm terms are involved right here. 2 logarithm terms involved. There's a logarithm of an x minus 2, and there's a logarithm of an x minus 3. Okay, let's find the domain of this function. But yes, thankfully, and see, for something like this, using an explanation through the transformation will not work because the transformation was limited to just within the family of logarithmic functions only, and then from the logarithmic function as a parent, and then we're going to use some linear transformations, and we turn things around, we shift things around, but this thing here is completely out of the family like that. And so that's why I used the transformations earlier to give some explanation, to give some insight, and then I have to switch your attention over to doing some actual mathematical work with that. And this mathematical understanding or explanation will be the main key, the major understanding for any of these problems where we find the domain of a function where logarithm is involved. Okay, so we got two logarithm terms. So we got one of them here. It's an expression. It's one expression inside a logarithm. We have another one here. So we have two expressions. So we have to, so here according to the logic, we have to ensure both of these are positive. Okay, so now we have two things to ensure, not only one. So we always have to ensure the expression inside a log, inside another log. This is the expression inside this log here. This is another expression inside another log right there. That's why we need to ensure one thing. The x minus 2 has to be positive. That's one of them. And we need to ensure further x minus 3 is also positive. We want to find an x value zone. We want to find a domain of x values where both of these are insured. Both of these are insured. Okay, and so now in that way, even though it's two requirements, but we can work on each one of these individually, and then we're going to combine the overall domains together. So on this particular requirement right here, x minus 2 needs to be greater than 0. I can add 2 to both sides, and that comes out x greater than 2. So on one requirement, x value must be, any x value must be greater than 2 to meet that requirement that this expression x minus 2 is positive to be inside of a logarithm. Okay, and now for the other requirements, I need to ensure x minus 3 greater than 0. So right from that requirement, I can just now add 3 from both sides, because if we require x minus 3 greater than 0, then adding 3 from both sides, we're going to lead to x greater than 3. So this is another requirement. We want to ensure x greater than 3 so that this requirement is also satisfied. All right, so now as far as requirements, we need to ensure x greater than 2 and x greater than 3. I'm yelling it out loud here. X greater than 2 and x greater than 3. So two separate requirements, but in the end, they need to exist together. They need to coexist. They need to exist together because this is one function. This is one function. So how do we bring in a combined domain right here? Think about the graph. The graph on the x-axis, on the line of real numbers. Okay, I'm going to draw two lines of real numbers side by side right here. There's 2 right here. There's 3 right here. Okay. On one graph, it says we want to be anywhere greater than 2, and excluding x equals 2. And on another graph, on the other hand right here, we want to be, okay, and I'm going to be shading the other way, and I want to be also still excluding 2. So think about if we blend these together, if we combine these together, the only satisfying integral, the only satisfying interval is, now let me draw that picture here. See, if I think about if we superimpose the two pictures here together in one. So there's a 2 here and there's a 3 here. Okay, I don't want to include 2, so I'm excluding 2. The shading to the right hand side of 2 goes like this. Okay, but now superimposing here, I have another exclusion point at 3, and I'm shading to the right hand side of 3. But the shading goes the other way. So now superimposing the two pictures here, the two pictures being put together, this is the only region where we want. This is the only zone that we really want. This zone right here does not have the overlap, so it's not indicating and right here. So because see, if we pick like a 2.5 here, x equals 2.5 will work for this one, but still fails the other one. X equals 2.5 is right here in this zone between 2 and 3. And so I just now pointed that out. X equals 2.5 works with this one, passes this one, but fails the other one, making this function, this term here undefined. So it makes the whole function undefined. And so that's why as an overall domain, we want the final satisfying domain is any x values that's greater than 3 right here, in this picture right here. So now with that argument, now we can come up with the final domain right here. All right, so now I can put away this picture. So now the domain, final domain of this function. All right, is going to be anywhere between between 3 and positive infinity. All right, it's x between positive infinity. All right, so that's how we tackle down a problem like this, and finding domain of any function where logarithm is involved, or multiple logarithms are involved. All right.